Okay, good afternoon, everybody, and thank you for joining. So this is the third session on our self-training course, Earth Observation for Official Statistics. And this is going to be around advanced applications of Earth observation, really trying to take what we've done in the previous editions and give you a flavour of what can be done. So before we start, just a couple of house rules. To anticipate the question that everybody always asks, yes, the session will be recorded and the slides and the recording will be shared afterwards by email and will also be on our page. And we do also make available some additional resources, which will be again on the webpage. We will send this out afterwards. Other than that, this is meant to be quite an interactive session. So we do have presentations, but at the end of each block, there will be a slot for questions. If you have a question, please just put it in the chat and we'll answer it at the end of each presentation. In terms of the agenda, this is the welcome, so welcome. I'll then just say a few words about overview of Earth observation applications. We're then going to dive into 3 specific use cases, and we have 3 presenters here to join us here. So on agricultural statistics, ecosystem accounting, and wetland inventories. And then at the end, I will also just say a few words about what comes next with this engagement between the Earth observation and statistical communities and how we would like to continue to build those relationships. And okay, this is me. I'm Phil Harwood. I'm the project manager of the ESA Stakeholder Engagement Facility. We support ESA with their stakeholder engagement, as the name suggests, and this network series is being organised in that framework. So, for those of you who have joined us, I think that you have been convinced by using Earth observation for official statistics, or you wouldn't be here. It's an open approach, it's free data, it's global, it's acquired consistently, it has local resolution, frequent updates, provides long-term time series for trend analysis, it's traceable, transparent, reproducible, and it has clear uncertainty levels. And this is not just coming from us. Obviously, we are in the Earth observation community, we are evangelists for the benefits of Earth observation, but this has actually been recognised. And this is from about 5 years ago now, where the DGINS actually recognised the benefits of Earth observation in official statistics and put out this Warsaw Memorandum to really try to encourage the uptake of Earth observation. Now, if you've been following the webinar series so far, you will know that you can do a lot of different things with Earth observation. It is more than just taking pictures from space. By analysing the data we received, we can estimate many, many different types of physical properties. But, and it's an important but, just being able to measure it does not necessarily mean it is immediately ready for use as a statistical source. There are steps to go through. And this is a figure that I took from Eurostat, just showing the different layers, starting from the acquiring of the data, the tidying it up, making it into analysis-ready data. Sometimes you're not actually measuring the thing you want to know, you're actually measuring a proxy for it. And then from there, you need to go to the product, you need to go to the statistics. And at every stage, you really need to be thinking about the ground truth in order to check your workings. This is just another example of how that works in practice at the different steps. Again, I took this from Eurostat, how you get from the raw data to a statistic on the different types of crop. And really, this is the sort of subjects that we want to discuss today, how we get from that raw image to a real statistical product through some examples. Now, there are operational services out there who do provide quality control updates. The most relevant ones are really the ones coming from the Copernicus service. This is an example of the Copernicus Land Monitoring Service and the dynamic land cover that they produce every few years. But there are more services from there, and they do provide quite a range of parameters around land, ocean, emergency, climate change, and so on. You then also have more research and development products, like the sort that are coming out of ESA projects, where you're looking at advanced land cover mapping, advanced cereal crop monitoring, or key atmospheric pollutants, topsoil organic carbon, many, many more. Now, I say these are R&D, but they're not completely R&D. Each of these has a lot of effort put into it in order to ensure the quality control and the robustness of the results. But what differentiates them from the operational services is that they are not produced systematically. They have been produced for some demonstration areas or some demonstration times. But in addition, there have also been several projects in the past that have looked at actually building the pipelines to produce operational statistics. This is a particular example from Statistics Poland, where they have started from sentinel measurements and used this to derive the condition of green areas within Polish cities. Not only is there vegetation, but what condition is this vegetation in? And how does that impact the well-being of the people around? Another example here is air quality in Greece. That figure on the left there, which shows just 3 areas within Greece, that's how the Greek reporting used to be done. But then using Earth observation data together with a set of in situ measurements, you were able to combine the high temporal frequency but low spatial of the in situ with the low temporal frequency but high spatial coverage of the Earth observation measurements to produce much more detailed statistics on NO2 concentrations at a municipality level. And this method was developed in Greece, but it was actually also applied to Poland as well, just to show the reproducibility of this. Now, I don't want to talk too much about this. I just wanted to give you a flavor, because we are now going to go into the detailed discussions of some of the cases where this has been done. But I do want to give a few take-home messages to think about during the presentations. One is, and this has been a consistent theme of what we've discussed so far in this series, there are many properties you can derive from Earth observation data, whether it's direct or an estimate via a proxy. You don't need to do it from scratch. There are many existing project resources already out there that you can reuse. Some of these are operationally produced, others more experimental. Some are experimental, still very, very highly quality controlled. So it's very important to understand the details of what you are using and the degree of quality control applied. And finally, the real take-home message, which I think is really what we're trying to achieve with this webinar series, is that we really need co-design. We really need the people producing the data and the services working together with the people who will use it in order to ensure a fit-for-use solution. Now, that was fairly generic. So what we would like to do now is to go into some details and show you some examples of where that we have really tried to take these principles and apply them to some real cases. Our first application use case is on Cenfostat. It is on advanced agricultural statistics. And I would like to introduce Sophie Bontemps from the University of Louvain, who will present on behalf of the Cenfostat consortium. Sophie, please.
Thank you, Phil, and good afternoon, everyone. So my name is Sophie from the University of Louvain, Belgium, and it's a pleasure to be here with you to present you the Cenfostat toolbox that we have developed. So using Earth observation data for agriculture is not a new ambition. I would say it's even a very old objective, but it has not been reachable since years, even if the theoretical framework was there. Today, things have changed. Why? Because of the Copernicus and IT evolutions that we have seen over the past years. So with the Copernicus mission, that you have heard about it during the past webinars, I'm sure, so the Sentinel-1 and Sentinel-2 mission in particular, we now have the data that match the requirements for monitoring agriculture at the field level. And these data are free, open, and ensured in the long term, so they are there for operational applications. Besides the EO data, we also have the IT infrastructure that is available to process this big data. And this is also a big change, again, to allow operational applications with the use of EO data. So you can buy servers, or you can even go on the cloud. This is feasible. The third component I would like to highlight is also what we call the in situ on the ground data. If you want to use remote sensing data to do maps or to do modeling, you need to have ground data to train or to calibrate the model. And so far, this has been the bottleneck. So they were not the quality and the quantity of these in situ data were not high enough to support operational nationwide application. But again, with the new technologies like the application on the tablets, on the mobiles, the UAVs, this is also very improving. And with these three evolution, we are in a point where EO data can now be a reliable and operational data source for national crop statistics. And with Sen4Stat, we have developed a toolbox, which was funded by the European Space Agency, which embed the processing algorithm to facilitate the use of this EO data by national statistical offices. And this is what I will present today. So this is the common approach without EO for crop statistic production. I will not be very long on these slides because probably you know it much better than me. But basically the way crop statistics are estimated without EO is that there is a survey which is designed, can be an area frame, list frame, point frame. Enumerators go to the field, or farmers answer forms, electronic forms, and the data that they've been collected are quality controlled, they are discussed, interpreted at the office, and then the statistics are published. What we have shown and what we have demonstrated in the Sen4Stat project is that we can use satellite observation as a complementary data source to field surveys to improve the stat. And this is very important. We consider the EO not to replace the field surveys, but to complement these field data, this survey data, to improve the statistics. And this is this approach that is illustrated here and that explains the rationale of the Sen4Stat toolbox. So the toolbox, so this is what we can see here. This is on a server on the cloud. It is making use of Sentinel-1 and Sentinel-2 data, and also of the surveys that comes from the NSO. And it is generating what we called EO products. It can be maps, it can be metrics that will assess how the crops are growing. It can be yield estimation. And when we have these EO products, Sen4Stat will combine these products with the survey data to improve the statistics. And there are different ways to improve. The first one, that is probably the most impactful, is what we call the cost efficiency. It means that if you are integrating EO product with the surveys, you will in fact increase the accuracy, the precision of the estimates. You will lower the confidence interval associated with the estimation. EO data can also have an impact on the granularity of the statistics, meaning that there can be estimates over a smaller administrative level, so you improve the granularity, and you also improve the timeliness, so you can get forecast. A last statistical impact is about the sampling design. As soon as you have maps, you can improve the allocation of the samples when you are doing your survey. There is a fifth impact, which is related to the data that are collected. EO data can have an impact on the survey protocol and also on the quality assessment of the data that have been collected. And the last impact is what I call downstream application. And what is meant here is that as soon as you get a map or as you get a yield estimation, you can use this data in a lot of other applications which are not strictly speaking statistics, like drought monitoring, flood monitoring, disease, insurance. But I mean, I will not discuss that today, but this is good to know that it can also have different purposes. So this slide is just to show that this is a toolbox. The outcome of the project is not a map. What we propose here is the processing tool that will play with the Sentinel data, Sentinel-1, Sentinel-2, and that will give you a set of remote sensing products. It is using in situ data that come from the survey, and it is combining, integrating the survey and the EO products with in the different applications that they have just mentioned. Within the project, we have implemented Senforstat in different countries, pilot countries. We have been working with national statistical offices in Europe, in Africa, in Asia. And in the next slides, what I will show you is some examples of the key impacts we had working in these countries. And I will focus in Europe, where Spain was our pilot country. So the first impact is what we call the cost efficiency, so using EO data to maximize the statistics accuracy. So we have been working in Spain, where the statistical data are coming from ESIRSE, which is an integrated list and area frame survey. And so we had this survey from the year 2020. And you can see here the kind of data we get from the survey. So areas of the different crop types and estimation of the yield coming from the ground. The traditional way the estimates are done is that the data are collected in ESIRSE, and that there is an inference. And so here, this is an example for the 3 main crops in Castilla y León, which is one of the main productive regions in Spain. As soon as you integrate the EO component, you will do a map, crop type map. You can see that the overall accuracy is of 85%, so it's good, but it is not 99%. So 85 is a standard accuracy, and you will integrate this map with the ESIRSE data, with the survey through a regression estimator. And what you can see here is, in fact, that you get some new estimation, which are more or less on the same order of magnitude, but what is more interesting, is that when you integrate the EO data, you increase the estimation precision, so you lower the confidence interval associated with the estimation. This has been shown for the accurate estimate, but also for the yield. Still in Spain, for the barley yield estimation in Castilla y León, the main message of the slide is here, where you get the yield estimation using only the survey data and the yield estimation when you integrate EO. You can see that the standard deviation associated with the yield estimation is significantly reduced, while the values remain comparable. So we are in the same order of magnitude. So again, the added value is also for the yield. The second impact was about the granularity. So if we look at an example in Spain, so this is a table where you can see the barley acreage estimate at the municipality level, so very small granularity. And you can see that the coefficient of variation is in most of the case less than 20%, which was considered as the acceptable level by the NSO. And so this is possible only because you get the map, an exhaustive coverage wall-to-wall of the area. Another example that we had is in Pakistan, so outside of Europe, where we did the wheat estimate. And here are the districts of the Sindh province. And you can see that for some districts, we had very few samples or even no samples in the survey. But we could still estimate the acreage through specific models targeting small area estimation. So this is just to show the added value of having a map if you have samples that are very complicated to visit, or sometimes in case of insecurity, for instance, or also if you want to decrease the number of samples to be visited. Then we go to the timeliness. So when I said that you can get forecast, if you look here on the left, you see a graphic that shows the accuracy of the map evolving over time for the main crops. And so June is the middle of the season. And what you can see is that as soon as you go in July, so 1 month after the middle of the season, the accuracy becomes stable. It is reaching a kind of plateau. It means that within the season, 1 month after the middle of the season, you can have a very reliable forecast of what will be the accurate estimates. And so this has been done in Spain, but also in Pakistan and in Zimbabwe, where we were able to deliver accurate estimates in the year of the season, so end of 2024 for the main season 2024. The last application is really about the sampling design. So having crop maps allows moving, for instance, from a list frame to an integrated list and area frame survey, but it is also used to improve the area frame. And here we are back to Spain. We were asked to do an irrigation map, so to see if the crops were irrigated or not, because the NSO wanted to integrate this characteristic in their sampling design. And so this is the kind of refinement that you can get using remote sensing data, for instance. The last aspect, which is not purely statistics, but which is very important, is the quality, the data. So when you integrate remote sensing data, as I said, you need survey data to calibrate the models or the algorithms. And so there are some minimum requirements that are needed. And so they are listed here. You need ground observation that are georeferenced at the field level, not at the household level. You really need the crop geolocalization. You also need to have a minimum number of samples for marginal crops and also a minimum number of samples for the non-crops. So this is something that can have an impact on the protocol. Having said that, your data can also improve and can also be beneficial for your survey because it will allow you a better quality control of the data. So it's able to detect how the polygon is homogeneous or not, if the crop that has been mentioned in the survey is correct or not. So there are some steps that really increase the reliability of the data. So these were some examples of how the integration of remote sensing data can increase the accuracy of the statistics. Of course, in making this change, adopting this new technology is it's not easy. It takes time. It requires really going step by step, I would say. This is what we learned from the experience we had with the pilot countries. And also it requires capacity building. And this is just to show that this is something that we have invested a lot. And so we have some experience in that. And we would be happy to share our experience with you. And with that, I close my presentation and thank you very much for your attention.
Thank you, Sophie. Before we move on, can we have any questions, please? Please ask them in the chat. Otherwise, in the meantime, I will just ask one question myself. So you mentioned about the use of the sampling, the tool for sample design, in order to make sure that you can apply. Are there any other difficulties in applying the Cenfostat in different countries? So, for example, you've applied this in Spain. How easy would it be to, say, apply it in Italy or France or Germany? What would be the steps required?
So there is no specific constraint in terms of sampling design. We have been working in countries where we have Spain has an integrated list and area frame, but also it is working in just simple list frame survey. So, I mean, for us, the most important is to have the georeference information at the crop level. And this is something that, of course, is easier with the area frame, because with the area frame, this is fixed in space, but you can get it also with a list frame. I mean, the sampling frame is not the constraint. This is really more the way you collect the data and you georeference them.
Okay, thank you. And in the meantime, actually, two people are asking the same question, which is a very practical one, around how complicated it is to start using the Cenfostat tool and whether there is any training on it.
So there are so complicated. So there are different parts in Cenfostat. Strictly speaking, from the EO point of view, so the toolbox is there. You can download it, you can install, and you can start using it. So there are some tutorials and documentation on the website. Of course, it requires to have a minimum of background in remote sensing. So this is when we are working with NSO, this is maybe the first step that to be sure that we have the good profile. But I would say that it's not only EO, it's only really the integration of the product with the survey with the statistics. And that it takes a bit more of time to customize the approach to the specific needs. But the first steps are not complicated. It is thought to be a toolbox that is working with a simple graphical interface, and this is a kind of click button approach. You don't need to code, you don't need to download yourself the data. You can just use the interface to do that.
Okay, great. And I think in your slides, oh, sorry, there's another question.
Yeah, I wanted to ask, maybe there is some kind of training planned in future for like to explain people how they can start using it, or there is nothing now planned.
So we work on the basis of the demands. So if there is a demand to have an online training, we can organize it. So we did a training at European Space Agency at Frascati in Rome in November. So sometimes it's online, sometimes we can do it physically. It really depends on the opportunities, but having something online is always feasible, and we can record and put it online, available after. Yeah.
Okay.
And whom people should contact in case, or like who organizations should contact in case they want to request such a training or a consultation?
So there are two options. Either you contact me directly, I'm the project manager of Send4Stat, or you go on the website and there is a contact form and you can go there.
Great, thank you.
I was just also saying, when we get to the end as well, we are going to be sending out a survey after this webinar to collect feedback on what people would like of the next steps. So feel free to request it as part of the survey as well, and we will pass it along to Sophie and to Isa. So, but thank you, Sophie. I think we'd better move on. If there's any other questions, please do feel free to raise them in the chat. We can still answer them even after the presentation is over. So with that, I would now like to call on Alessio Bourcain. I hope I pronounced that correctly, by the way. I forgot to ask. If we could get your slides up, please. Alessio has been working on the People Ecosystem Accounting project, and he is going to present the project to us and how Earth observation has been used to support ecosystem accounting across Europe for different national statistical officers. So Alessio, please.
Hello, good afternoon, everyone. Can you see correctly my slides?
Yes.
Perfect. Okay. So good morning and good afternoon, everyone. My name is Alessio. I work in the BAS Center for Climate Change. Is a research center located in Bilbao. And I'm working in the ARIAS team that stands for Artificial Intelligence for the Environment and Sustainability. But I'm here today on behalf of the consortium that developed the People EA project. I'm going to explain over the presentation what this is about. Basically, this was a collaboration between the ARIAS team, the VITO, that is also part of the OpenEO team, and this project was financed by the European Space Agency. Just let me put the second slide. I'm not sure how familiar you are with environmental accounting, so I'm just going to give a quick background of the history and information of this framework. The main framework was developed by the United Nations, and is the System of Environmental Economic Accounting. This framework was initially meant to integrate information for consistent with the national statistics, traditional national statistics, and the SIA Central Framework was the first milestone that was adopted in 2012. Then it was added.
Sorry, Alessio, can I just interrupt one moment? Can I just ask you maybe to put your screen on full screen, because I think we see the full document at the moment. Thank you. Sorry for interrupting.
No problem. Let me try to do this again then.
I think if you share not the whole screen but a tab where you have that presentation, it will work. It will be the fastest way.
Is this working now better or not? Not yet.
It's fine. I think let's just continue. We can see it.
Okay, sorry if and so yeah, this is the main framework that was developed was the SIA Center framework. Then there was also another framework dedicated to ecosystem accounting. It was the first time that it was done, and it has a heavily spatial explicit approach that was not something that was common to obtain in combination with statistics. For this, there were 3 years of experimentation, and then in 2021, this became a standard also adopted by the United Nations. The project that I'm going to present is specific for Europe, so I also want to have a brief overview of what has been done in Europe over the last decades in these regards. And I think that the main basically regulation or milestone that is important is the regulation of 2011 on ecosystem accounting, which require National Statistical Office to adopt new models for ecosystem accounts, which include tracking ecosystem extent, service, and condition. If you're not familiar with that, slowly in the next slides, I'm going to show you quickly what it means. And this integration aims to enhance the measurement and reporting of natural capital and its economic value, supporting better environmental policy making. The statistical approach used in this project is different from what has been traditionally used. A more traditional common workflow could be the one that is referred as reference implementation, which generate results using statistical inputs and offline Earth observation pre-processing. This approach, it's easy to run whenever the data is already available and is ready for use, but it's limited for complex model like big data, for example. And the PeopleEA demonstrator instead uses on-the-fly Earth observation processing, making the observation and the estimate scalable and automatic. And in this case, we also face different challenges, which are mainly achieving statistical acceptance and adoption of the results. This being a new approach, we invested heavily in collaboration with countries to make sure that the results produced were also accepted by the national statistical offices. And to achieve the scalability and automation that was described before, this project was achieved via technological partnership between the ARES team and the Vito team. The ARES team is the one that provides the technology that uses semantic reasoning to select the best combination of data and models that are available in the network for a specific context and to advance a specific methodology. Instead, the Vito team at OpenEO provides a powerful computational platform with availability of a large number of Earth observation data. So the combination of these two technology enhanced the overall results from this partnership. And just quickly, for those unfamiliar with ARES, which stands for Artificial Intelligence for the Environment and Sustainability, it's a modeling platform whose most relevant application in the context of environmental accounting is the ARES for SIA. There was an application built in collaboration with the United Nations to generate results consistent with the SIA methods for all countries around the globe. Anyone can just connect to the browser, select their country, and select the accounts that want to estimate, and receive maps and tables which are basically available for all countries around the globe. And this is also the reason why we teamed up with Vito, since we had experience in this field. But for the People EA objective, say that the goal is different. The main goal was to review the opportunities and challenges for integrated Earth observation in environmental accounts. And this integration was focused on national ecosystem accounting and particularly focused in the European context. The project developed and validated what we call EO for ecosystem accounting demonstrator accounts. And it involved close participation with National Statistical Office and environmental agencies in the country that for which we produce results, which I'm going to show you in a second. I think that the key output, along with the application that countries can use to estimate environmental accounts, is also research and development roadmap for future Earth observation integrated solution, assuring continuous improvement on the work that we do. And these are the 6 accounts to showcase the use of Earth observation, developing collaboration with Greece, Italy, Netherlands, Norway, and Slovakia. In this particular presentation, I'm going to focus on forest condition accounts, but I have also in the backup slide information about the other accounts in case you are interested to see what was this process and how results were obtained. And so in the People EA project, we focused on the European continent, and we applied different methodology. The integration between ARIES and OpenEO enabled the assessment of forest ecosystems in Europe on different premises than before the project. We started basing our model on a regional study from Maes and colleagues, but these were only 2 temporal observations, initial and final, in the year 2000 and 2018. So we implemented the same methodology, leveraging on the availability of observation data for Europe, covering the same period, but making it available this result at an annual level and with a higher resolution and available to the users basically with a single click. And for this specific work, we identified 40 forest types as a result of the combination of the CORIN classification of forest and also 11 biogeographic regions provided by the European Environmental Agency. And for each variable, the variable being basically the raw information that we use to identify the status of a particular ecosystem. For this variable, we use a computational workflow of an indicator that is observed extracting its original value from the data set over the spatial and temporal context observed. Then for each variable and for each ecosystem type, we extracted sort of the good and bad conditions for each forest type. Good condition were considered the values in the 98th percentile of that forest typology over Europe, and bad condition were considered the 2nd percentile for that particular variable in that type of forest. This is very important because one of the greatest challenge in the past was to actually be able to set this threshold. As there is always say a lot of discussion among ecologists on which should be the correct threshold for this type of analysis. And in this case, using this methodology allows a consistent representation of the condition of forest in Europe. This indicator were then obtained both on the upper and lower reference values, and they were disaggregated by type of ecosystems. Also in this case, the raw values are rescaled between 0 and 1, so as to obtain in these indicators that are comparable, since the original information of the variables may come, with different range of values. So after that, what we do is we compute the forest condition index, which quantifies the forest health by summarizing the information of several indicators accounts, each representing a different aspect of the forest condition. The indicators composing the index aim to represent as comprehensively as possible the components of the ecosystems, which are abiotic, biotic, and the landscape. And the index is composed of a single indicator for each ecosystem typology class. Since the variables belonging to the same ecosystem typology are usually highly correlated. So we take into account this fact when using the spatial explicit data. And the indicators were then prioritized and selected according to their relevance and their direct relationship to map forest conditions, but also their availability of data for their measurement, including their spatial resolution and temporal resolution. So how often this data is updated. And in the end, the results are summarized also in a table, which is very important for statistical purposes, since the majority of the National Statistical Office is more interested in this result and more used to use tabular data rather than dealing with spatial explicit information. For this reason, basically, the system provides full information about the workflow and the combination of data and models that have been used. Everything is documented and transparent, but also provides, let's say, a very easy to interpret final results with a summary table. And there is also a report that explains potential caveats or limitations in how the data should be interpreted. So the initial forest condition accounts can include up to 6 user-selected matrix belonging to the 4 ecosystem class typology that you see on the upper right. And it shown below with global data sources, which are automatically replaced by local data where available. This is the part that is taken care by the ARIES, basically integrated modeling platform, which automatically select the best data and model for a specific context. So here you see that the user accounts was compiled using 3 yearly average to smooth out potential seasonal or yearly effect. In order to obtain meaningful forest ecosystem condition indicators, the data must often be adapted from the original collected temporal resolution and aggregated into annual observation. Also, depending on the indicator, this has been done before the data were placed in our system by calculating the averages and the value of the remote sensing observation over the course of the year. Nevertheless, there is always the possibility to change this transformation in case there is reason to believe that a different average should be used over a particular place. And basically, compared to the original implementation, these accounts offer 3 main advantages that have higher spatial and temporal resolution. There are clearly improvements that can be also more easily and maintained and improved over time, since the results are built on the fly. This means that whenever new data becomes available and the user goes into the platform and select a particular account, it always gets the latest available information. And also in terms of cost, I would say, since we use a technology that is established, the ARIES one, the cost of maintenance for an application is also very low, since let's say that the core elements, all the ecological information that is then used by the application is directly maintained by our team for different projects. So in this case, we managed to, let's say, obtain economies of scale. And all the results, as mentioned before, and this is very important, are fully documented, transparent, and replicable, which I think is very important, especially since we use artificial intelligence. That is now, there are concerns about how transparent or what is the actual workflow that occurs before one of these technologies spit out a result, where this is something that we care a lot in our technology, and we try to be as transparent and make sure that each result is fully replicable. And this allows also experts to be able to improve on the current methodology, and also to users to point out things that are not working so that we can easily improve on them. So the People-EA project demonstrated the potential for Earth's observation for ecosystem accounting. EO provides benefits like large area coverage, frequent updates, and more spatial detail. A successful integration required knowledge and processing tools such as web-based option like the People-EA or some GIS platform. But if you want, we can discuss this later. I think that the latter in this case is much more advantage, because a user can really access the data without having knowledge about or GIS expertise, nor knowledge about any coding. Also in this case is basically the user can obtain the results through simple clicks in the interface. And EO integration for extent and condition accounts continues also with the WIT project. That is a project dedicated to mapping the world ecosystem extent dynamic. And definitely further research is needed for service accounts to match pure statistical approaches. But also in this project, we are also integrating in situ data, which are the missing step in this workflow to complete and to make it even more robust. So we start from statistical information with spatial explicit analysis, and then we also integrate this with in situ on the ground data. This is all. Thank you very much for your attention, and I'm very happy to take any question if you have any.
Thank you, Alessio. Very good. I see one question in the chat, but actually I'm going to ask a question myself first, if I may. Because I remember the People Ecosystem Accounting Project, there was great interest and there was a very high involvement from the national statistical officers concerned. But has there been any follow-on that you're aware of with the statistical officers directly in terms of their uptake of your methods and solutions?
Yes, I think that there has been some change, and I think one of the main barrier in the past in relation to the work that we were doing is that, especially this is also true at a global level, in which you need to produce results where there is not really good data or the model are not perfect. And I think with the new wave of satellite basically project that on a constant base derives more information at granularity that was not even thinkable 5 or 10 years ago. I think this has really improved the ability to generate such results with more consistency and for longer time series and with a greater resolution. Then there is still the work that needs to be done in close collaboration with statistical office to confirm that the results generated make sense and are statistically relevant. And I think, this is something that we need to keep working on. But I think it's also more often the case that there are this capacity built within the National Statistical Office, because they realize that that is something that it's important also in their line of work. So basically what we try to do is to also ease this basically, the work that National Statistical Office needs to do with this data.
Okay. And once again, just for the people listening, there will be a questionnaire afterwards. I mentioned for Sophie that if you're interested in the Centre for Stat training, please do let us know. But also if you might be interested in more training on this particular aspect of ecosystem accounting, please do let us know in that, so that we just need to know what you need, basically. There was also a question in the chat, actually, just a very quick question. You mentioned the R&D roadmap, the things that need to be done further. Is that publicly available? And if so, where can we find it?
Yes, there is. I think this should be available. We have a website for the People EA project, and I think the roadmap is available there. I'm gonna now try to share the link in the chat for this.
Okay, great.
Yeah. But I want to say that basically this was a project that was about 2 years ago, and now we're already in another project still financed by the European Space Agency, also in cooperation with Vito. And we're actually working on the World Ecosystem Extend Dynamics. So that's basically the implementation of the R&D map that we set 2 years ago. So you can also, if you're interested, you can also check this project.
Okay, great. Yeah, if you could drop the links into the chat, that would be useful. And of course, we'll circulate them afterwards. Okay, I don't see any more questions in the chat, but if there are any further questions, please do just share them. So I would now like to give an example of the SDGs, because this is actually a key field in general of interest to statistical officers as SDGs, but we haven't really touched on them. So I would like to invite Christian Toltrup from DHI to present to us on water-related ecosystem and the SDGs. So Christian, all yours. Thank you.
Thank you, Philip. And do you hear me fine?
Yes, we do.
Okay, thank you. Yeah, thanks for that introduction. And just for background, so my, you can say, role in this SDG reporting has been to support the data science and reporting on SDG 661, which covers the change in water-related ecosystems. So I went one too fast there. And again, just reminding about the history on the SDGs, which was, indicator framework that was developed back in, I think, 2016 or 17. And basically under this framework, countries committed to measure, monitor, and report progress on 17 targets more than 150 indicators. A lot of these indicators is related to the environment, and quite early it was realized that traditional, you can say, statistical sources would not cover the full extent of these environmental indicators, and they needed to be complemented with, you can say, non-traditional data sources like Earth observation and related geospatial information. And one good example on a indicator where lack of data was quite evident very early on is indicator 661 on the changes in both the extent but also quality of water-related ecosystems. So to make the indicator as informative as possible, I mean, it's disaggregated into different sub-indicators related to surface waters, to wetlands, to water quality, and river flow is actually also something that has been added in over time. As with the other indicators, a UN agency has a custodian role in terms of helping countries to monitor and advance the progress on the indicator. So back in 2017, when the first SDG data drive was launched, the UN Environment Program, who is the custodian for the indicator here, reached out to countries and asked them to feedback countries on the state and trends in the freshwater ecosystems. But in essence, very few countries was able to provide any data, and those who did provide data, they were quite poor in terms of the temporal and spatial coverage. So clearly something needed to be done in order to be able to report on this indicator globally. So the response from UNEP was to look to the major space agencies and tech organization to see how Earth observation could potentially fill this role. So you basically have the workflow which then manifested itself where you have the satellite data providers from NASA, the European Space Agency, and JAXA, who is providing free and open satellite data, which basically for most and all of them is actually ingested into big data analytic platforms. And key for the SDG process has been Google Earth Engine, who has provided a lot of support in terms of providing the processing framework and the data access to the raw satellite data, and which is used by a number of key technology partners, the Joint Research Center here in Europe producing global surface water trends, the Global Mangrove Alliance, who's providing the information on coastal wetland ecosystems, and ourselves in DHI, who's doing stuff related to inland wetlands and river flow modeling. And all this data has been, compiled at a global level and put together in an online visualization and reporting tool, which we refer to as the SDG 661 app or the Freshwater Ecosystem Explorer. These data from these global data sources is now on an annual basis being updated into the system, and then every 3 year there's a reporting cycle where we try and analyze the data and to give a sense of the state of the freshwater ecosystems in the world. And the latest reporting that we did was back in 2021, I think, and there will be a new one coming up this year. But at that time, I mean, we found some quite significant, you can say, issues, and basically, in summary, I mean, showing that at least half the world's country, have some level of degradation taking place in their freshwater ecosystems. So this is, of course, something that kind of called for action, and it may also point to the dual role that you can see Earth observation data having in this implementation of the SDG agenda, because one is to do this monitoring and evaluation and reporting at the global level. The other part is actually to be able to drive decisions and make changes on the ground. And in that sense, and in these global data sources, which are really nice and excellent in pointing to some global trends and issues, they may not always, have the right accuracy when you zoom into national or local level. They can have biases, and therefore there can be some shortcomings for national or subnational policy and action planning. And this is at least some background why the European Space Agency was launching the project Earth Observation for Wetland Inventories, which is an attempt to try and fully exploit the increased capabilities that the latest generations of free of open satellite data have to provide better information on wetlands, and at the same time also advancing the tools that could be adopted by national stakeholders to independently undertake wetland inventorying with satellite data. We are, or the project is aligning the outcome of these wetland inventories with the IUCN Global Ecosystem Typology. And in doing so, it actually helps support and align with a number of different policies, including the SDGs, the Ramsar Convention on Wetlands, the UN Ecosystem Accounting System, as we just heard about, and the Convention on Biological Diversity. The solution that we are developing and which we hope can be adopted by countries in principle quite simple. It's about acquiring the satellite data and some labels that we can jointly use to train a machine learning algorithm to output these wetland typologies at the national level. It's of course a little bit more advanced when you look into it. One of the key problems is actually the labels, because the whole reason for launching the project is that there's this huge information gap when it comes to available data in countries on wetlands and freshwater ecosystems. So how do you get labels from you could say non-existing information? And here we're advancing a little bit because there's a parallel work going on trying to develop a global wetland inventory based on the same principle, but which, as I said, will inevitably, when it comes later this year, have this, you can say, national bias. But our suggestions and hope is it is sufficient to provide the initial, you can say, labels to train an optimized model, which can be complemented by users' own data when available, and then we can generate these national training data sets together with the required multi-sensor satellite input data and ultimately train an optimized, a nationally optimized model. And we're expecting this to all happening in an open, you can say, accessible framework. So for users, it will be free to access, but only the cost associated with processing the data will be something that needs to be covered. Right now, we are demonstrating this with a number of pilot countries. So we have Italy, Algeria, Kenya, Colombia, plus Madagascar in the pool of pilot countries. And most advanced we are with Italy, where we have produced, first full national scale map according to this proposed framework. And the hope is that compared to the global data sources that we were starting from, that we will have output here which deliver improved land use, land cover accounts for national and global reporting obligations within countries, but also that we have data and information which is at a level where we can support national wetland conservation and restoration efforts. We are still in the process of fully validating these outputs, but so far they seem to stand the eye test. They look quite nice when we compare to local maps from specific settings, but the challenge is to get a good, you can say, accuracy number across the full country. And again, we are challenged by the fact that this is new information, so we don't have the validation for all the classes, so we need to find ways to work with national experts on getting a good validation data set prepared. So the takeaway messages here is that, you do have these regular Earth observation data, which are excellent to monitor and report on many environmental ecosystem and by example here also on freshwater ecosystems. There are global data sets available which serves a purpose for the broad scale reporting and trends identification, but there is a need to also develop tools that can be appropriated by users and help, drive national, subnational decision making. And it is to really within the realm of countries today to take on this exercise, leaning into new big data infrastructures that allow this type of processing. And basically, this is what we hope to prove with the Earth observation for wetland inventory projects, and ultimately leading, to better progress reporting and to make better management decisions. And just ending up on, I think I had one more slide that puts this into kind of the broader role of Earth observation in the whole SDG reporting framework, where we came from these global data sets and, metadata and methodological guidelines around this to this, challenge on really, putting the ownership back to the countries and developing these national tools that can be adopted and used by countries to develop improved information on a range of different indicators, including the 661 as demonstrated here. Of course, it needs to come with the open access tools and the associated guidelines and capacity building. So it's is also in the pipeline. So I think that would be my last concluding slide.
Thank you, Christian. Thank you very much indeed. Okay, so anybody who has any questions for Christian, please put it in the chat. I see a quick one there, but it was already answered, so I think we skipped that one.
Yeah.
Christian, well, maybe I'll just go first, Natalia, because I had one question for Christian, which is, you mentioned the machine learning that you were using, and I think Alessio alluded to the fact that machine learning is maybe still not quite trusted within the statistical community. What would be your feeling here? Do you think that people are receptive to this sort of approach for the SDGs?
Yeah, I think you're hitting the crew of the matter. Of course, it will depend on the accuracies that we can come up with. And I mean, the challenge we do have is to actually get these credible reference data that can prove that the machine learning model is returning the output that we hope and expect. Sometimes it's easier than others. I mean, we have been working in the domain with national forest inventory data, which is available. You have good national data that you can run and test your model on. Here, it's more challenging because you simply don't have that information for the wetland typologies at national scale in most countries, really.
Okay, thank you. Natalia, you wanted to come in as well with a question?
I would like to ask, so the final output, the final product of this project, it will be some kind of toolbox or tool in general, or it's going to be some kind of map? And if it's going to be a map or a data set, how often it's going to be updated, or updating this data set is not considered like within this project?
The project will, I think the tool here is crucial, and then we will provide these national demonstrations for our pilot countries to kind of be the proof of concept. And but with the tool, you can say you have the possibility to apply this to new countries, and you have control over the update frequency you want to run with it. So the tool is key here, but of course we need to have the evidence that the tool produces the expected outcomes that come through these pilot countries I was mentioning, including Italy.
And when it's going to be shared with wide public? Yeah,
the hope is it will be mid this year, so another half a year from launch is the hope. Yeah.
Thank you.
Okay, great. I don't see any more questions in the chat other than the one that's in. I should say we're running slightly ahead of time. So if anybody does have any general questions or questions for the speakers, please do drop them in the chat. But in the meantime, I wanted to just talk a little bit about what comes next, because this webinar series was something that we've been doing together with the European Space Agency and coordinating with a few other statistical actors. But we don't want to just do a webinar series and leave it there. We would like to really use this to start building some more bridges between the statistical and Earth observation communities. So if we could go to the next slide, please, Luke. And I will try to answer the question, what next? So the first thing is that we really hope that you found this training course useful. But don't just tell us that. Please fill in the survey that we will send out. The QR code is here. But this is partly feedback on the course itself, what you liked, what you didn't like, what you think we should have covered, but also thoughts on what you would like to see next. This could be things that maybe you want us to cover in a webinar, or maybe you would like us to cover something in training. It could be something broad about Earth observation, or it could be specific things like if you need training on specific tools, such as the ones that Sophie or Alessio presented. Please, it's open. Just put in your thoughts about what you would like to see between the interface between Earth observation and statistics. Now, we are going to be providing what we call some deep dive sessions in the next couple of months. What this means is that we would like to talk one-on-one with some of the statistical officers, mainly to understand what you're doing and what you would like to do with Earth observation, where you've got to, what you would like to do, and try to identify opportunities where we can do some working together. This could mean support from my team, the Stakeholder Expansion Facility team, or it could be building the connections with the Earth observation community in general, putting you in touch with specific people who can help you with your specific issues. Again, if you are interested, please contact us directly or complete the feedback and it will all be in there. There will be some additional training to follow later in 2026, but the scope of this is really pending both the feedback we get, but also the discussions we do in the deep dive. So the better feedback we get, the more accurately we can tailor this. Now, one other thing, we mentioned this in the very first of this webinar series, is that there is this upcoming Statio event on the 5th and 7th of May 2026. This really is intended as bringing together the Earth observation and statistical communities on a very equal basis, each side setting the agenda, topics it wants to discuss. So the abstract deadline for this is the 31st of January, which is tomorrow. So if you haven't already done so, please stay overnight. Stay up overnight and write your abstract and get it in there before the deadline. And then after that, the registrations for attendance will open on the 1st of March, and we really hope to see many of you there. We've also put together a list of further resources. This is around Earth observation, but also around where you can find more information on Earth observation and statistics, both for us, but also from Eurostat. Some basic resources for Earth observation data access, and also where you can find a list of the ESA projects and what they are producing. Again, we really hope that they are useful. And then the very final thing is that we really do encourage you to get in touch with us anytime. This is my email here, but also the general CEF team, and also some QR codes linking to our website and to our LinkedIn page. Please do follow us there. Please do get in touch at any time and discuss. Okay, we're a bit earlier than scheduled, but I don't see any questions in the chat. So unless anybody has any burning issues that they really need to get off their chest, I think we will probably leave it here. I would really like to say thank you to everybody for contributing, to Sophie, to Alessio, to Christian, to very especially to Natalia, who has basically single-handedly got us through the first 2 editions of this, and also to the audience. I really hope we will be in touch. I hope to see many of you in Frascati in May, and if not, I hope you see you another time. So thank you very much and goodbye.
Thank you. Bye-bye.
Bye-bye.
Thank you.
Thank you.